We'll wait for others to join. All right, welcome everyone to the week 11 tutorial of thermodynamics. So in previous tutorial, we have finished up with uh, the pure substances, and towards the last we were at the Maxwell relations. And I hope you all are regular to your lecture videos by the prof on the Nptel portal, as well as you are regular to your assignments. We are approaching towards the end of this course. So those who have registered for the exams, your exam is also gonna be scheduled very soon. I hope you guys have received the dates. So let us start with week 11. Let me share my screen. Yeah. I hope my screen is visible. All right, I'm also visible now. Great. So let us go into the continuation from the previous thermodynamic relation topic. So let's start with the TDS relation. Okay. Incorporate the Maxwell relations in that. Okay. First is temperature entropy relations. Let's come to the first TDS equation which we have done earlier. First TDS equation. So our first TDS equation was TDS is equal to du plus PdV. Du plus PdV. Okay, so ds can be written if you transpose this t on the right hand side. Du by t plus PdV by t. Okay. And what is du? Du is nothing but cv dt. Since du is cv dt, so you can write ds as cv dt by t plus, and p by t can be written as, and from the gas law, p by t is equal to r by v. So this p by t can be written as r by v dv. All right, r by v dv, or I can dv by, all right, in this manner. So if you observe here, entropy is function of temperature as well as volume. Entropy is function of temperature as well as volume. From this implies your entropy is function of, I should not use this, is function of temperature comma volume for a real gas, for a real gas. For an ideal gas, it is only a function of temperature. But when a real gas is there, it's a function of temperature and volume. So from the chain rule, if I do the differentiation, ds, entropy is a function. So ds will be dou s by dou t dt at constant volume, when volume is constant, and when temperature is constant, it is dou s by dou v at constant temperature Tv. Okay. All right. Now also you multiply with T on both the sides. Okay. Multiply with T on both sides. What will you get in the above equation? In above equation. So what will you get? TDS equal to T time dou S by dou T at constant volume dt plus T dou S by dou V at constant volume or constant temperature D. Okay. Clear? Any doubts in here? Okay. So if no doubts, since if we say our volume is constant, okay, then your equation, this is the first kind of relationship. Okay. If your volume is constant, since TDS is equal to du plus PdV. If your volume is constant, then this term goes away at constant volume. All right. Now, What can you write? So if you observe one thing here, you have this relationship here, and you have this relationship which you have got from it. Okay? Now, if you want to compare the two terms, what will you get? Let us see. So at constant volume, ds can be written as cv dt by t. All right. Since again I'll write du can be written as cv dt. Okay. And if you compare this term with this term with this term, okay, you compare the, or you can directly say as well this in this manner as well. If you compare this and this, because both are entropy change only at constant volume. Okay, both are entropy change at constant volumes, at constant volume. So your TDS right here on comparison, T dou S by dou T is nothing but on comparison of coefficients. All right. And from the Maxwell relationship, which we have discussed in the previous tutorial, since dou S by dou V at constant temperature can be written as dou P by dou T at constant volume. Dou S by dou V at constant temperature is dou P by dou T at constant volume. Okay. So you can put this value and finally get your relation, that is TDS I'm saying this relation. It can be written as this relation in the equation dou S by dou V from the Maxwell relation can be written as dou P by dou T at constant volume. Okay. Now put this both the values in equation in this equation. I'll write here which equation I'm talking about. Put above two values, above value in equation 1. What will you get? TDS is nothing but CV dt. Okay. T dou S by dou T can be written as CV plus your term dou S by dou V can be written as dou P by dou T at constant volume T. Okay, at constant volume. Got it? This is your relation in terms of Maxwell relations. Equation in terms of Maxwell relation. Okay. Any doubts in this? TDS is nothing but CV dt. So what I have done in whole is that I have my first equation TDS equal to du plus PdV. So it can be written as ds is equal to CV dt by t plus r dv by v. Because we know that du is CV dt and p by t can be written as r by v. Now we know that entropy is a function of temperature and volume for a real gas. So ds can be written as dou S by dou T dt plus dou S by dou V dv at constant volume and temperature respectively. Now you will multiply with t on both the sides. You got your equation 1. Now you have to manipulate the coefficient, these two coefficients, this one, to get these value of the coefficients of dt and dv, that is the partial fraction values in terms of Maxwell relationship. Okay. Since we know that because it's a constant volume process, so when you do a constant volume in here, you get your first coefficient as Cv by T dt. Okay. So if you put this dt by T, if you compare the, or you can say that this value can be compared to this, that is Cv by T. Okay. All right. So that is your value is equal to Cv itself. So you got that value for the first coefficient at constant volume. You got this coefficient value in terms of Cv. Now this coefficient will come in terms of Maxwell relation, because you know that from Maxwell relation, dou S by dou V at constant temperature is dou P by dou T at constant volume. Now put this relation in here, this in this value as dou P by dou T. So you finally got Cv dt plus T dou P by dou T at constant volume. All right. Any doubts? Now let's come to the another relation. Second TDS. Second TDS equation. So what was our second relation? That was in terms of enthalpy. First was in terms of entropy. Sorry, internal energy. Second is in terms of enthalpy. TDS is equal to dH minus PdT. Okay. So ds can be written as dH by T minus V by T dP. Now, since you know that dH can be written as Cp dt, and from the gas law, V by T can be written as R by P. So put the values. So your entropy becomes Cp dt by T minus R by P or R dP by P. R dP by. All right. Any doubts? So from here, what we get that our entropy is a function of temperature and pressure. Entropy is a function of temperature and pressure. So therefore, entropy is a function of temperature and pressure again for a real gas. For a real gas. But for ideal gas, it's only a function of temperature. So again, by the chain rule, you can write the differentiation ds as dou S by dou T at constant pressure dt plus dou S by, sorry, not d, dt plus dou S by dou P at constant temperature dP. Okay. Now again, you will multiply with T on both the sides. On both sides in above equation. So it will be TdS T dou S by dou T at constant pressure dt plus TdS or T dou S by dou P at constant temperature dP. Okay. Now again, you want these two coefficients, this value and this value, how you will get. So we know that since it's a constant pressure, first coefficient is constant pressure. So since TdS is dH minus VdP, so for constant pressure, this will be 0. Okay. So your dH can be written as TdS is nothing but Cp dt. All right. Clear? like we did in earlier case. So from here, ds was cv dt by t. So from here, ds will be cp dt by t. Okay. So from here on comparison, you can say that TDS, like we did here, the comparison. On comparison of coefficient, T dou s by dou t is equal to CV. T dou s by dou t is equal to CV. Dou s by dou t at constant volume earlier. Sorry, I missed this constant volume. And here it is dou s by dou t at constant pressure. So T dou s by dou t at constant pressure is nothing but Cp. Okay, you got the first coefficient. Similarly, from the Maxwell relation, okay, I should write here on comparing the coefficient. And from the Maxwell relation, dou s by dou p at constant temperature is nothing but negative of dou v by dou t at constant pressure. You got the second one as well. Now you put this, if you say that this equation is equation number 2, put above values. In equation 2, we get our final TDS expression. TDS is nothing but Cp dt minus T dou v by dou t at constant pressure dp. This is your equation. All right. These are your two equations which you have got. Okay. These are the two equations which you have. So in the second TDS relation, what I did, this time your TDS relation is in terms of dH minus VdP. Take the T on the right hand side. ds is Cp dt minus R dP by P. So from here, for our real gas, entropy is a function of temperature and pressure. ds, you apply the chain rule. For the partial fraction can be written, ds can be written as dou s by dou t dt at constant pressure. Other time, temperature will be constant, dou s by dou t dt. So you multiply by t on both the sides in above equation. You have TDS is T dou s by dou t at constant pressure dP plus T dou s by dou p at constant pressure T, constant temperature dP. Okay. Now for the first, you want both of these coefficients. So for the first coefficient, it's a constant pressure. So TDS is equal to dH minus VdP. You put the dP 0 for constant pressure. You get your first coefficient from here on comparison, that is Cp. And for the second coefficient from the Maxwell relation, dou s by dou p at constant temperature can be written as dou v by dou t at constant pressure. Put this value, you get TDS is Cp dt minus T dou v by dou t dp. All right. I hope is it clear. Any doubts? So both the relation are more or less same. In previous relation, it was Cv, it was a positive sign. It was V here and P here and V here. Okay. All right. Any doubts? Okay. Just give me a minute. All right. So now let us come to the concept of volumetric expansivity. Okay, volume expansivity. So what is volume expansivity? It's basically measure of a fractional change in volume of a substance, okay, per unit temperature rise. Per unit temperature rise, okay. It tells that how much a substance expands or contracts with temperature changes. So volume expand or volume changes because of the temperature, okay, at constant pressure if we say. And because of that, how much is the volumetric change in the at in a substance, like there is a gas. From the name volume expansivity, so how the volume change at constant pressure because of the temperature, and what is the volumetric change in. Let me write here. It is a measure of fractional change in fractional change in volume of a substance per unit temperature rise. Okay, which indicates how much a substance expands or contracts, okay, with temperature changes. So the symbol for this is beta. So you can write beta as volumetric change, that is dV by V, that of temperature rise at constant pressure. So I can write this 1 by V dV by T constant pressure. Okay. Volumetric change dV by V for a per unit temperature rise at constant pressure. Okay. So by the name, it is a measure of fractional change in the volume of a substance per unit temperature. Now let us come to isothermal compressibility. Compressibility. And it is denoted by KT. Okay, KT. So it's basically defined by the fractional or differential change in the volume due to change in pressure. Previous one, expansivity, was change in volume with respect to temperature. This is change in volume with respect to pressure. So I should write it is defined as defined by the fractional change in volume due to change in pressure. Okay, change in pressure. So what is compressibility? I'm not saying isothermal compressibility. Compressibility is inverse of bulk modulus. Inverse of bulk modulus. And what is bulk modulus? It is nothing but change in pressure to that of volumetric strain. Let me first write step by step. Compressibility is nothing but 1 by bulk modulus. That is Bm. And what is Bm? That is one change in pressure to that of volumetric strain. That is dV by V. Okay. So compressibility can be written as, put this value. Therefore, compressibility is inverse of 1 by is dP by dV by V. So it's nothing but 1 by dP dV by V. Okay. So what is isothermal compressibility? Or you can at constant pressure or constant temperature. Isothermal at constant temperature. You can itself write, take out V outside, and this is your compressibility. So isothermal will be, so therefore isothermal compressibility your KT is nothing but 1 by V dV by dP at constant temperature. This is your proof as well. Okay, we have proved this relation as well. So we know what is volume expansivity, what is isothermal compressibility, we know the Maxwell relations, we know Helios equation in terms of that as well. Now I'll give you one proof to do. It's very, very important one to do, and it will take time for you, but you have to think. Okay, you have to think here, and you have to get back with this proof. Okay. Prove Cp minus Cv is nothing but temperature, volume, beta square, that is expansivity by kT, isothermal compressibility. You have to prove this. Okay, and this eventually involves a real gas. It's not an ideal gas I'm only talking about. Okay, so you have to prove this. All the terms notation we have discussed. Take your time, think on it. I will get it, and I'll discuss in a few minutes. All right. I guess few of you have got. So let us do the solution to this proof. So we have derived two TDS equation. The equation this equation. Okay, let us use these equations. Okay, so let us say this is equation number 1, and this is equation number 2. Let us compare because both are representing TDS only. Okay. Let us compare equation 1 and 2 from above. Okay, because both are TDS. So that is CV dt plus T dou P by dou T at constant volume dP dV is equal to Cp dt minus T times dou V by dou T at constant pressure dP. Okay, take Cp and Cv together. So you get rearrange Cp dt minus Cv dt is nothing but T dou P by dou T at constant volume dV plus T dou V by dou T at constant pressure dP. Okay, clear? Now you take out dt common. So this can be written as Cp minus Cv times dt. Again, right hand side remains like this. Plus T dou V by dou T at P. So your dt can be written as T by Cp minus Cv dou P by dou T V dV plus T upon Cp minus Cv dou V by dou T P dP. Okay, I've taken this on the right hand side. Just simple. So now if you see, your temperature is a function of volume and pressure. Okay. Since temperature is a function of pressure and volume. Okay. Now do the differentiation of this. So you can say dt can be written as dou T by dou P at constant volume dP. Sorry. Right. And dou T by dou V at constant pressure dV. Okay. Now you again will compare your coefficients between the above equation. You have your equation. This is your equation A. Let me use some other color. This is your equation A, and this is your equation B. Now you will compare because both are dTs only. This is dt, this is dt. Okay. This is dV, this is dV, and this is dP, and this is dP. So you will compare this with this, and this with this. All right. Let us compare one by one each of these coefficient. Let us see which coefficient we want to compare. Okay. So first coefficient is dou T by dou V. Okay, this coefficient I'm comparing. This coefficient is of dV, so this will compare with this. Okay. On compare coefficients, compare of dV of equation A and B. So that is T by Cp minus Cv, dou P by dou T at constant volume is nothing but dou T by dou V at constant pressure. Okay. So from here you can take out Cp minus Cv is nothing but you transpose this on the right hand side and you will get eventually your Cp minus Cv comes out to be T times dou V by dou T at constant pressure and dou P by dou T at constant volume. Okay. Then we did one relation in our previous tutorial. Our theorem is there. But in one of the theorem, since T is function of pressure and volume, we know that. So product of the three partial differentials is equal to negative of 1. So that, what do I mean? dt dou T by dou P at constant volume produced with dou P by dou V at constant temperature with dou V by dou T at constant pressure is nothing but your negative of -1. So from here, because you want this value, you will get from dou P by dou T from here. Okay. And you will put that. Let us see. So this implies your dou P by dou T at constant volume is nothing but negative of dou P by dou V at constant temperature and dou V by dou T at constant pressure. Now put this okay. Put this here. So you'll get dou P by dou T at constant volume. Therefore, you can say that using this in above. Therefore, Cp minus Cv is equal to minus T times dou P by dou V at constant temperature into negative of dou P by dou V at constant temperature into dou V by dou T at constant pressure. Okay, clear? Any doubts? Dou V by dou T. Oh, sorry. Dou V by dou T at constant pressure. Mistake. So this was T into dou V by dou T. T into dou V by dou T at constant pressure. Okay, after putting. Now this term and this term is same, this and this, so we'll do the square. So therefore, Cp minus Cv is nothing but minus T times dou P by dou V at constant temperature times dou V by dou T at constant pressure square. But still you have not got your final answer. It is TV beta square by KT. We have to first write this in terms these values correctly. Okay. Also, if we want to see, I put a short question here. to prove that CP is always greater than CV. I write a short question here. Let me take from this relation. Prove that value of CP is always greater than CV. Use this relation, take a minute and think that how you will prove a short question inside this. Then we will proceed further. Okay. Okay, I think it is pretty simple. I just gave you 2 to 3 minutes to think. See, a short solution to this is, since if you see in the above relation Cp minus Cv, if volume change is positive, temperature is always positive. Okay, T is positive. You see one by one each term. Temperature is positive. If volume is positive, pressure is negative, because pressure and volume are inversely related as per the gas law. Okay, and this term will always be positive because it's a square. Okay, so T is positive. Second term, dou P by dou V at constant temperature is always negative. And other term, dou V by dou T square at constant pressure is always positive in above equation. All right. That is, therefore, Cp minus Cv is nothing but negative, this negative sign. Then temperature is positive, positive. Then this other term is negative. We saw. Again, it is negative. And last term is positive. That is. So negative, positive, negative, positive. So it's overall positive. So this is always greater than 0. Okay. This whole term is positive always. So Cp minus Cv is greater than 0. This implies Cp is always greater than C. Proved. Hence proved. Okay. This was a very short question, but we are still left with the question to prove our initial relation which we want. Okay. So in this equation, we need two of the values. So we know that what is volume expansivity. Since volume expansivity beta, as we have seen, is nothing but 1 by V dV by dt, dou V by dt, constant pressure. Okay. So you can write dou V by dou T, dou V by dou T at constant pressure can be written as V times beta. You got this value, dou V by dou T value got. Okay, beta v beta. Okay, and since we know that isothermal compressibility, since isothermal compressibility kT is nothing but minus 1 by V dou V by dou P at constant temperature. Okay, dou V by dou T at constant temperature. So from here, dou V by dou P at constant temperature can be written as minus kT times V. Okay, put these two values in above equation. Suppose this equation is equation number 3. Okay, and put, have we defined AB anywhere? We have defined. So we'll say it as C and D. C and D. Put C and D in equation 3. Okay, so you will get Cp minus Cv is nothing but minus T times dou P by dou V is nothing but minus 1 by Kt into V. Since dou V by dou P, just take an inverse, it will be minus 1 by Kt into minus Kt into V. And dou V by dou T is your beta into V. Is nothing but beta into V. Final relation comes out to be minus T, minus and minus become positive. Okay. So let's write it as T by Kt into V into beta square V square. So this V and V cancels out. So therefore, your final relation Cp minus Cv is nothing but Tv beta square by that was required to prove. Hence, proved. Very important relationship. Okay. Very, very for any real gas. I hope it is clear, pretty much clear. Okay. So I'll give a brief context that how we came to it. We have already derived equation 1 and 2, those tedious equation, this equation 2 and this equation 1. Okay, both are tedious, so we'll compare both of them. So on comparison, we'll compare T1 and 2. So we got Cp minus Cv in terms into dt is equal to the right hand side after transpose. We got the dt from here. Okay, and we got an equation. So from here we got to know that temperature is a function of volume and pressure. Temperature is a function of volume and pressure. Okay, temperature is a function of volume and pressure. So by applying the chain rule, you get dTs in this term. So you compare equation A and B coefficients of dV. Okay, so from here you get Cp minus Cv in terms of T dou V by dou T, dou P by dou T at constant. Now you want to get both the values. Since temperature is a function of pressure and volume, so we have done one theorem. Okay. Since temperature is a function of pressure and volume, we have done one theorem that product of these three partial differential is equal to negative of 1. So from here we got dou P by dou T in terms of dou P by dou V and dou V by dou T and put this value in above. So from here we got Cp minus Cv in terms of negative of T dou P by dou V at constant temperature, dou V by dou T at constant pressure square. We got our equation 3. From here I ask you that prove that Cp is always greater than Cv. How can we prove that? Since if you see first term T is always positive, second term will always be negative because if pressure increases, volume increases, pressure decreases, both are inversely proportion. And other last term is a square value, so it's always going to be positive. So in the above equation, if you put this Cp minus Cv is negative, product of negative, positive, negative, positive. So overall it's a positive one. So Cp minus Cv is greater than 0. So Cp is greater than Cv. Okay. Now we know that coming to our initial proof, what is volume expansivity? We know. So from here we got dou V by dou T as beta times V. And from the definition of isothermal compressibility, we got dou V by dou T at constant temperature as negative of Kt into. Put this C and D in your equation 3. This equation, this is your equation 3. Okay, put this here. To finally get your, after putting, to finally get your relation that is Cp minus Cv is equal to Tv beta square by T. That was very, very important. I hope there are no doubts remaining now. I've cleared it in a very simple way. Okay. Now let us come to a concept of Joule-Thomson coefficient or Joule-Kelvin effect. Joule-Thomson. Okay. Or you can say Joule-Kelvin effect. And this is represented by mu J. Okay. So it's basically it quantifies the temperature change of a gas during a pressure change at a constant enthalpy. Okay. Let me write here. It quantifies temperature change of a gas during a pressure change at constant enthalpy. Okay, at constant enthalpy. All right. That means there is no heat exchange. So it can be written as mu J is nothing but dou T by temperature change with respect to pressure change at constant enthalpy. Okay, please hold on. I'll be back in a minute. Okay, sorry for the interruption. Okay, so the Joule-Thomson coefficient is temperature change with respect to pressure change at constant enthalpy. Okay, so we'll derive this relation as well. So we know that from the TDS equation, your TDS equation is, we write first box set, since TDS is dH minus VdP. So from here, dH can be written as TdS plus VdP. Okay. Now we will use one of our equation in back, which we have derived, the equation number 2. Okay. This was your equation number 2. I'll again show you this equation TdS. Okay. Cp dt minus T dou V by dou T R d. Okay. And put this value in this above equation. In the equation this. Yeah. We'll get the value. Using equation 2 from above and put it in here. So dH will be Cp dt, okay, minus T dou V by dou T at constant pressure Tp plus your remaining term, that is VdP. Plus your remaining term, that is VdP. Okay. Now let me take dP and dt common terms. So this and this term separate and this term separate. So your dH can be written as Cp dt plus V minus T dou V by dou T at constant pressure dP. Okay, constant pressure. So if you observe, your enthalpy is a function of temperature and pressure. So from here, you can say that enthalpy is function of temperature and pressure. So for constant enthalpy, because your definition of Joule-Thomson coefficient is defined for a constant enthalpy. So for constant enthalpy, dH should be 0. dH is equal to 0. So equate the above equation to 0. So this implies, therefore, the above equation Cp dt plus V minus T times dou V by dou T at constant pressure with dP is equal to 0. Take this term on the right hand side. So Cp dt is nothing but negative of V minus T dou V by dou T at constant pressure dP. Okay. What was required? The ratio of dou T by dou P. Dou T by dou P. We have this and this. Your final equation at constant enthalpy comes out to be. Therefore, dou T by dou P at constant enthalpy is nothing but 1 by Cp into T dou V by dou T at constant pressure minus. This is your final relationship, which is required. This is your Joule-Thomson coefficient. Okay. There's a point to note here. Before note, I'll explain once again. Joule-Thomson coefficient is the thing, but it quantifies the temperature change of a gas with respect to pressure change for a constant enthalpy, isenthalpic process. That is mu j is nothing but dou T by dou P at constant enthalpy. Let's get the expression for this Joule-Thomson coefficient. Since we know that TdS is dH minus VdP equation, so here dH is TdS plus VdP. So using the equation 2, which we have derived earlier, and put the TdS value in this equation, you get dH as Cp dt minus T dou V by dou T dP plus VdP. Separate the dP and dt terms, okay? And for a constant enthalpy process, dH should be 0. So equate the above equation to 0, okay? And transpose it over the right hand side. Finally, you get the ratio dou T by dou P at constant enthalpy as 1 by Cp, T dou V by dou T, T dou V by dou T at constant pressure. This is your final expression for Joule-Thomson coefficient. This is nothing but your mu j. All right here. Or let us keep it like this only. Therefore, mu j is, expression for mu j is this. Okay. All right. The point to note here is that value of the Joule-Thomson coefficient for ideal gas is 0. For an ideal gas, is 0. You have to prove this. Take a minute, use this expression, think why for an ideal gas it will be 0. Okay, so value of Joule-Thomson coefficient mu j is 0 for ideal gas. We have to prove. That is proved. So constant enthalpy means isenthalpy. That is throttling process eventually. Okay, which we have already discussed in past, and we'll discuss further on today as well. Okay. So since PV is equal to RT for an ideal gas, okay, you differentiate it. So this will be PdV plus VdP is equal to RdT plus TdR. So it is a constant value, differentiation is 0, and dP will also be 0. Okay, so you are left with PdV is equal to RdT. So dV by dt is equal to R by P for a constant volume, constant pressure process. So from here, if you multiply both sides with T, dou V by dou T at constant pressure is T time TR by, okay, TR by, all right. dV by dt you got. Also, PV is equal to RT. This is also equal to P. This is equal to V. So you got the expression. Now put this expression in Joule-Thomson coefficient. Since mu j is nothing but we have derived the expression of mu j as 1 by Cp T dou V by dou T at constant pressure minus P. Put this expression here. So that is 1 by Cp V minus V, 0. Hence proof. Mu j is 0 for an ideal gas. Okay. Yeah. Next question. Prove that enthalpy of an ideal gas is a function of temperature. Of temperature. Okay. Prove this. Take 2-3 minutes and prove. Okay, let us discuss. So if you use the equation of the expression of mu j. Okay. So what was the expression of mu j? In that derivation, we had an expression. This was an expression. Okay, this one. Suppose this is equation number 4. Okay, use this equation number 4. Using equation number 4, the equation was dH is equal to Cp dt plus V minus T times dou V by dou T at constant pressure times dP. Okay, so for an ideal gas, PV is equal to RT. So here from here, PdV differentiate PdV plus VdP RdT plus TdR. So again, this and this is 0 for a constant pressure. So from here, PdV is equal to RdT. Oh, oh, I am doing RdT. So from here, dV by dt, or you can say dou V by dou T at constant pressure can be written as R by, if you multiply with T on both sides. Okay, multiply with T on both sides. So this is RT by V. That is nothing but again volume you have seen. So put this expression in here. Dou V by dou T at P. So that is, therefore, dH is Cp dt plus V minus T times dou V by dou T at P into dP. So that will be, no, I should not write like this. I should write V minus V dP, and that is 0 eventually. So dH is Cp dt, hence proved. It is function of temperature only for an ideal gas. Hence proved. Okay. Next, we have to prove that internal energy for an ideal gas is a function of temperature. Okay, do this. Take few minutes and do it. Okay, let us prove that. So from the TDS equation, TDS is du plus PdV. Okay, so from here internal energy can be written as minus PdV. Okay, now what you do, you use the equation number 1 which we derived. Use the equation number 1 which we derived. Okay, minus PdV. So and put that TDS value in here using equation 1 from above and put in this term. Okay, so du can be written as cv dt plus t dou p by dou t at constant volume dv, and your remaining term minus pdv. Okay, now separate out the coefficient of v and v together. So that is cv dt plus t dou p by dou t v minus p tv. That is your internal energy du. Now again, you know, for ideal gas, PV is equal to RT, and differentiate. Since it's a constant volume for differentiation, so it is PdV plus VdP is equal to RdT plus TdR. So this term is 0 and constant volume, so this term is 0. So from here, VdP is RdT. So from here you can say that. Multiply with T on both the sides. So you get T times dou P by dou T at constant volume is nothing but TR by V, that is nothing but your P. And put this expression in here. So your final TU comes out to be, therefore, your internal energy can be written as CVDT plus P minus P dV. So therefore, du is your internal energy is function of temperature only for an ideal gas. Hence, true. So in crux, we can say that we can note here that enthalpy is function of temperature, internal energy is function of temperature only for ideal gas. Okay, second point, enthalpy is function of temperature and pressure, and internal energy is function of temperature and volume for real gas. Okay, And third point is that Joule-Thomson coefficient value mu j is 0 for ideal gas. For ideal gas. We have proved everything. Okay. All right. So I think we can end here. And in the next tutorial, we'll discuss further and do questions. And probably that will be our last tutorial in the next session. Okay. So this is week 11. And by week 12, we'll finish up with our course of thermodynamics. So those who have enrolled for the course on the NPTL, you will get a sheet, as you all get so far, where the link of this recording of this tutorial is available, as well as the link for the PDF notes, that is the Google Drive link, is available where I upload all these notes. Those who are seeing this video for the first ever time, so this is on my YouTube channel. My YouTube channel name is NPTEL with Varnit. Okay, this is my YouTube channel, and in there are all the recordings available in the playlist of thermodynamics, and the PDF notes Google Drive link is in every video description. Okay. Okay. So I hope you all remain regular to your tutorials as well as lectures and assignments. Exam is coming soon for this course. Those who have registered for the exam. So uh, start preparing towards your revisions. And I'll see you in the next tutorial. Thank you so much.